Right now, at this exact moment, there are two numbers that describe the universe you are sitting in. They disagree with each other, and by every rule of physics, we know they should not. One of them says the universe is expanding at about 67. The other says about 73. Same universe, same laws, more than a century of extraordinarily careful work standing behind both of them. For over a decade, the sharpest people in cosmology have been trying to make one of those numbers go away. They have hunted for a mistake in the telescopes, a mistake in the stars, a mistake in the math. And the number will not move. The man at the center of this already has a Nobel Prize. He won it for a discovery so strange that when he first found it, he assumed he had broken something. His name is Adam Rees, an astronomer at Johns Hopkins University, and he has spent most of his career measuring how fast the universe is flying apart. His argument, stripped down to its simplest form, is this: the lower number is not a measurement of our universe at all. It is a prediction produced by a model describing a universe that may not be the one we live in. We are not comparing two measurements. We are comparing one measurement against one assumption, and the assumption is losing. That claim would be easy to dismiss, except for what has happened since the James Webb Space Telescope opened its eye. Webb was the machine that was supposed to end this. It was sharper than anything before it, sharp enough to see through the crowding that everyone suspected was corrupting Rees's data. Point it at the same stars, and the error would finally show itself. Webb looked, then it looked again, then it looked with 3 different methods in different galaxies, using different kinds of stars, and every single time it agreed with him. There are 3 things you need to know before this makes sense. One is a discovery in 1998 that a young researcher spent months trying to disprove because he thought it was too absurd to publish. One is the reason a number from a satellite mapping the oldest light in existence was never really a measurement at all. And one is happening in about 5 weeks on a launch pad in Florida, where a machine is being prepared that could end this argument for good. Start with the numbers themselves, because they sound like nonsense until someone translates them. When astronomers say the universe is expanding at 73, they are using a unit that hides how simple the idea is. The full unit is kilometers per second per megaparsec. A megaparsec is a distance, roughly 3.3 million light years, which is a little more than the gap between our galaxy and Andromeda. So the number means this: a galaxy 1 megaparsec away is moving from us at about 73 kilometers every second. A galaxy twice as far moves twice as fast. 3 times as far, 3 times as fast. That is the whole idea. Space itself is stretching, and the farther apart 2 things are, the more stretching lies between them. Nothing is flying away through space. Space is growing between everything. The number attached to that stretching is called the Hubble constant, and it is arguably the most important number in cosmology. It sets the age of the universe. It anchors almost every distance we quote for anything beyond our own galaxy. Now here is why a gap between 67 and 73 is not a rounding error. That difference is about 8 or 9%. In most sciences, predicting something to within 9% would be a triumph. But cosmology has spent 30 years driving its uncertainties down to the 1% range. When your error bars shrink to almost nothing, and your answers still refuse to meet, you no longer have a disagreement. You have a contradiction. And taken on its own, the higher number would make the universe roughly 1 billion years younger than the standard model says it is. 1 billion years. Missing, depending on which number you trust. To understand why this fight matters, you have to go back to 1998 and do a project that was expected to produce a boring, tidy answer. At the time, cosmologists were confident about one thing. The universe was expanding, and gravity was slowing that expansion down. Every galaxy pulls on every other galaxy. The only real question was how much the expansion was decelerating, and whether it would eventually stop and reverse. 2 rival teams set out to measure the slowdown. One was led by Saul Perlmutter in California. The other, the High Z Supernova Search Team, included Brian Schmidt in Australia, and a young researcher named Adam Rees. Their method was elegant: find exploding stars called Type 1 a supernovae in very distant galaxies. These explosions happen when a dead stellar core pulls in enough material to detonate, and they all detonate at almost exactly the same brightness. Astronomers call them standard candles. If you know how bright something truly is, and you measure how dim it looks, you know how far away it is. Find enough of them at enough distances, and you can chart how the expansion has changed over billions of years. In the autumn of 1997, Rees ran the analysis. The answer that came back was not a slowdown. It was not even 0. The equations were telling him that the universe was dominated by something with negative mass. Negative mass does not exist. So his first conclusion was the obvious one. He had made a mistake. He went back through the code, the calibrations, the assumptions, hunting for the error, because a result that strange is almost always a bug rather than a discovery. The error never appeared. What appeared instead was a different explanation. If you put back a term Einstein had introduced and later abandoned, a cosmological constant, a kind of energy woven into empty space that pushes outward instead of pulling in, the numbers snapped into place. The universe was not slowing down, it was speeding up. Rees later described the result as surprising, shocking even. Brian Schmidt checked the work himself and said his own reaction sat somewhere between amazement and horror. His former advisor emailed in January of 1998, warning him not to go public with a claim that enormous. Another colleague, Nick Suntzeff, pushed the other way and told him that if he was really sure, he needed to publish immediately. 60 days later, they published. Perlmutter's team reached the same conclusion independently. Science magazine named it the breakthrough of the year. That mysterious outward push is what we now call dark energy. It makes up most of the energy content of the universe. Nobody knows what it is. And its discovery earned Rees, Schmidt, and Perlmutter the Nobel Prize in Physics in 2011, which matters for what comes next. He has been here before. He has already found a number that should not exist, tried to kill it, and failed. This time, the number he cannot kill is 73. To measure how fast the universe expands today, you cannot use a single tool. No instrument reaches from your backyard to the edge of the visible universe. So astronomers built the cosmic distance ladder, and it works exactly like the name suggests. Each rung depends on the one below it. The bottom rung is pure geometry. For nearby stars, you can measure distance the same way your two eyes judge the distance to your hand. Watch a star from one side of Earth's orbit, then from the other side 6 months later, and it shifts slightly against the background. The size of that shift gives you the distance, with no assumptions at all. The second rung is a particular kind of star, and it is the reason this entire field exists. Cepheid variables are massive stars that pulse, brightening and dimming on a strict cycle. In 1912, an astronomer named Henrietta Swan Leavitt noticed that the slower a Cepheid pulses, the brighter it truly is. Time the pulse, and you know the star's real brightness. Compare that to how faint it looks, and you have its distance. Cepheids are bright enough to see in other galaxies, so you calibrate them using the geometric rung, then use them to measure galaxies far beyond it. The third rung is those same type 1A supernovae. They are visible across billions of light years, far past any individual star. So you find galaxies containing both Cepheids and a recorded supernova, use the Cepheids to fix the distance, then use that distance to calibrate the supernova brightness. Then you follow the supernovae outward, deep into the expanding universe. Geometry, then pulsing stars, then exploding stars. 3 rungs, each one handing off to the next. That is Rees's number. It is built from things you can actually see in this universe, right now. And every rung has been rebuilt and rechecked more times than almost any measurement in modern science, which brings us to where the other number comes from. And this is the part most people get wrong. The lower number, 67, does not come from watching galaxies at all. It comes from the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled just enough for atoms to form and for light to travel freely for the first time. That first light is still arriving, stretched by billions of years of expansion into faint microwaves that fill the entire sky. The European Space Agency's Planck satellite mapped that light with astonishing precision. Frozen into it are ripples, sound waves that were moving through the hot plasma of the infant universe when the light broke free. Those ripples have a characteristic size, set by how far sound could travel before everything froze out. That size acts as a ruler. Measure how large those ripples appear on the sky today, and you learn about the geometry and contents of the universe. But notice what you have measured. You have measured the universe as it was 380,000 years old. You have not measured how fast it is expanding now. To get from that ancient snapshot to a present-day expansion rate, you have to run the whole thing forward. You feed the early universe into the standard model of cosmology, built from ordinary matter, dark matter, and a dark energy that never changes. Then you let the equations run for nearly 14 billion years and read off what the expansion rate should be today. The answer that comes out is about 67. And this is Rees's entire point. That number is not an observation of the modern universe. It is the output of a model. It is a forecast. It is what the expansion rate has to be, if and only if every ingredient in the standard model is correct and complete. So when people say two measurements disagree, they are being imprecise. One side is a measurement, the other side is a prediction. And when a careful measurement disagrees with a confident prediction, the honest first suspect is not the measurement. Rees put it plainly when the Webb results came in. With measurement errors negated, he said, "What remains is the real and exciting possibility that we have misunderstood the universe." That is the claim at the center of this story. Not that the telescopes are wrong, that the model is describing a universe slightly different from ours. But for years, that was a minority view, because there was a much more comfortable explanation sitting right there. The comfortable explanation was crowding. Cepheid variables live inside galaxies, and galaxies are messy. When you photograph one from millions of light years away, the light of its neighbors can bleed into the same patch of your detector. If that happens, your Cepheid looks brighter than it truly is. If it looks brighter, you conclude it is closer. If your distances come out too short, your calculated expansion rate comes out too high, which would produce exactly the discrepancy everyone was arguing about. It was a clean, unglamorous, deeply plausible explanation. The tension was not new physics. It was blurry photographs. Hubble launched in 1990, and its vision has limits. Many respected astronomers believed this was the answer. Meanwhile, the gap kept widening. Physicists measure confidence in units called sigma, which describe how far a result sits from what chance alone could produce. 3 sigma is interesting. 5 sigma is the threshold at which particle physicists are permitted to announce a discovery. It corresponds to roughly a 1 in 3.5 million chance of a fluke. The Hubble tension crossed 5 sigma. Rees has described it as having passed the point where you stop arguing and simply say, something is going on here. But sigma only measures the odds against random chance. It says nothing about a systematic error, a flaw baked into your method that repeats every single time you use it. Crowding would be precisely that kind of flaw. More data would not fix it. More data would only make you more confident in the wrong answer. There was exactly one way to settle it. Build a telescope sharp enough to separate a Cepheid from its neighbors and look at the same stars again. That telescope launched on Christmas Day, 2021. The James Webb Space Telescope sees in the infrared, with a mirror far larger than Hubble's, and resolution that turns Hubble's crowded smears into individual points of light. If the crowding hypothesis was right, Webb would expose it immediately. The Cepheids would resolve, the contaminating neighbors would separate out, the stars would turn out fainter than Hubble had recorded, and the expansion rate would fall toward 67. Rees's team pointed Webb at more than 1,000 Cepheids across 6 galaxies, including a nearby galaxy whose distance is known from pure geometry, and 5 galaxies that had hosted recorded supernovae. Then they compared, star by star, against what Hubble had reported. The difference was essentially nothing. In the units astronomers use for brightness, the offset came out to about 1/100th of a magnitude, with an uncertainty 3 times larger than the offset itself. In plain language, Hubble had been right the whole time. The crowding correction had already been handled properly. The paper stated the result with unusual bluntness in its own title. Webb observations reject unrecognized crowding of Cepheid photometry as an explanation for the Hubble tension at 8.2 sigma confidence. Read that again, 8.2 sigma. The favorite explanation for the tension was not merely unsupported, it was ruled out with more statistical confidence than the tension itself had ever achieved. Rees said they had now spanned the whole range of what Hubble observed, and could rule out measurement error as the cause with very high confidence. The safety net was gone. And that is when the story stopped being about telescopes and started being about the model. But there is a serious objection that deserves to be taken seriously. Not everyone agrees with Adam Rees, and the person who disagrees most sharply is not a crank. Wendy Friedman is one of the most accomplished observational cosmologists alive. She led the original Hubble Space Telescope Key project that first pinned the expansion rate down to within about 10%, and she has spent decades on this exact problem. She also used Webb, and she got a different answer. Friedman's team deliberately avoided leaning on Cepheids alone. They used 2 other distance markers as independent checks. One is the tip of the red giant branch, based on the fact that aging stars reach a sharp, predictable peak, brightness, at the moment helium ignites in their cores. The other uses carbon-rich stars that glow with a consistent infrared brightness. 3 methods, 3 answers. The carbon stars gave about 68. The red giants gave about 70. Their Cepheids gave about 72. Averaged together, her team's headline figure came out near 70, close enough to the model's prediction that the tension would largely evaporate. Friedman's interpretation was direct. That spread, she said, is telling us there is some systematic error in one or more of the distance methods. Rees's response was equally direct. He argued that her study rested on a small supernova sample and gave a somewhat misleading impression. This is what a real scientific disagreement looks like. 2 highly credentialed teams, using the same telescope, on overlapping targets, arriving at different conclusions. Anyone who tells you the tension is completely settled is skipping this chapter. But the weight of evidence has shifted since then, and it has shifted in one direction. In December of 2024, Rees's team published a broader analysis using 3 separate distance methods, checking Webb against Hubble across a large sample of supernova host galaxies. Webb returned an expansion rate of about 72.6. Hubble, on the same targets, returned about 72.8. Two flagship observatories, built decades apart, with entirely different optics and detectors, agreeing with each other almost exactly, and both sitting 5 to 6 points above what the model predicts. With two NASA flagship telescopes now confirming each other's findings, Rees said, "We must take this problem very seriously." Then the confirmations started arriving from directions that have nothing to do with the distance ladder at all. In December of 2025, a team led by researchers at the University of Tokyo published a measurement using gravitational lensing. When a massive galaxy sits between us and a distant quasar, its gravity bends the quasar's light into multiple images, and light taking different paths arrives at different times, sometimes separated by weeks or months. Measure those delays, model the mass doing the bending, and the expansion rate falls out directly. No Cepheids, no supernovae, no ladder, a completely separate physical principle. Across 8 lensed systems, the answer came back near 73, with a precision of a few percent. As one of the lead researchers noted, the method is completely independent of the others, so systematic errors hiding in those methods cannot touch it. Then, in April of 2026, came the result that arguably closed the door. A large collaboration published a community consensus analysis of the local expansion rate, combining Cepheids, red giants, supernovae, and several other independent techniques into one framework at better than 1% precision. The answer was 73.5, give or take about 8/10. More importantly, the result held even when individual methods were removed from the analysis. In the collaboration's own words, the work effectively rules out explanations of the Hubble tension that rely on a single, overlooked error in local distance measurements. There is no longer one loose thread to pull. To make the tension disappear through error alone, you would now need several unrelated techniques to be wrong by similar amounts in the same direction, by coincidence. So if the local universe is not the problem is what happens between the beginning and now. And that is where the story gets stranger, because the most promising lead in cosmology right now makes everything worse. In the Arizona desert, an instrument called the Dark Energy Spectroscopic Instrument has been building the largest 3-dimensional map of the universe ever attempted. It captures the light of thousands of galaxies at once, measuring how far away each one is and tracing the structure of the cosmos across billions of years. By its second major data release in 2025, it had mapped nearly 15 million galaxies and quasars. And it found something that was not supposed to be there. The standard model assumes dark energy is a constant, fixed. The same density of outward push in every cubic meter of space, unchanged since the beginning, unchanged forever. That assumption is the anchor of modern cosmology. The map suggests dark energy may be weakening. Depending on which data sets you combine, the preference for a dark energy that changes over time reaches somewhere between roughly 2.8 and 4.2 sigma. That is short of the 5 sigma discovery threshold, and it must be said clearly that the strength of the signal depends on which supernova catalog you use. This is a hint, not a verdict, but it is a very loud hint. One of the project's co-spokespeople said it is looking more and more like we may need to modify the standard model of cosmology to make these different data sets make sense together. Here is the twist, and it is the reason this whole problem has become so uncomfortable. If dark energy is fading in the way the data suggests, then running the early universe forward through the corrected equations produces an even lower expansion rate today. The most exciting new result in cosmology does not close the gap. It widens it. So the field now has 2 independent cracks in the same wall, a measured expansion rate the model cannot produce, and a dark energy that may not be behaving the way the model requires. And the leading fix for one of them deepens the other, which brings us back to that launch pad in Florida. On the 30th of August, 2026, at 20 past 7 in the morning Eastern Time, a Falcon Heavy is scheduled to lift off from Kennedy Space Center carrying the Nancy Grace Roman Space Telescope. Roman has a mirror the same size as Hubble's, but a field of view about 100 times wider. It can survey the sky roughly 1,000 times faster. Over its mission, it is expected to map more than 1 billion galaxies, and it will build its own distance ladder from scratch, on its own hardware, with its own calibration. It is not alone. The Vera Rubin Observatory in Chile has begun operations, and Europe's Euclid mission is already returning data on the geometry of the cosmos. Rees has called these missions the cavalry. Within a few years, we will have expansion measurements from instruments that share almost no assumptions with the ones fighting today. Either the tension survives that, or it does not. And there is a decent chance the answer arrives while most of us are still alive to hear it. If you want to be there when that answer comes, the launch on the 30th of August is the moment this argument stops being theoretical. Subscribe and stay with this channel because when Roman returns its first distance measurements, this story either becomes the biggest revision to physics since Einstein or quietly collapses into a footnote. Either way, it is worth watching from the beginning, because we have been here before, twice, and the two previous times went in opposite directions. In the 1800s, astronomers noticed that Uranus was not orbiting where Newton's laws said it should. The discrepancy was small and stubborn and would not go away. Some argued the laws of gravity needed rewriting. Instead, a mathematician calculated where an unseen planet would have to be to explain the wobble, pointed a telescope at that spot, and found Neptune almost immediately. The model was fine. Something was simply missing from the inventory. Encouraged by that success, astronomers turned to another anomaly. Mercury's orbit was also drifting in a way Newton could not explain. So they went looking for another hidden planet closer to the sun. They even named it in advance: Vulcan. Vulcan was never found, because this time the model itself was broken. It took Einstein and general relativity a complete reconstruction of what gravity even is to explain Mercury's orbit. The anomaly was not a missing object. It was a missing idea. Rees has framed the current crisis in exactly those terms. Is this a Neptune, he has asked, or is this a general relativity? Nobody knows yet. It could be a new form of energy in the infant universe that briefly pushed harder and then vanished. It could be that dark energy has been slowly changing all along. It could be a property of dark matter, or something no one has thought of. Or it could be something as mundane and disappointing as a subtle flaw shared by several methods at once. But this is the part that should stay with you. For most of human history, we could not measure the universe at all. We guessed at the age of everything and got answers ranging from 10 to 20 billion years. Now we have driven the uncertainty down to within 1%, and the moment we did, the universe handed us a contradiction we cannot explain. That is not a failure. That is what precision buys you. You only discover that your map is wrong when your map gets good enough to be tested. Somewhere out there, light is still arriving from 380,000 years after the beginning, carrying a prediction about how fast everything should be flying apart today. And all around us, galaxies are moving away faster than that prediction allows. One of those two things is describing a universe that does not exist. We just do not know which one yet.